So we were here. We had remembered chosen only terms where n is equal to 1. So lambda is equal to 1.5. So all the terms contain 1 by square root of r. All stresses go to infinity as r tends to 0, and they go to infinity as 1 by square root of r. Moreover, if you look at the stresses, this is sigma r theta, that is the shear stress. So this is your r, this is your theta, and this is sigma r theta. And sigma r theta has to be antisymmetric for mode 1, which means that if you take the point which is a mirror image of this point, then sigma r theta has to be in the opposite sign. And here, if you look at the sigma r theta expression, this is an antisymmetric function. So this corresponds to mode 1, and this is a symmetric function which corresponds to mode 2. In the symmetric case, sigma theta theta, which is this stress, has to be symmetric, has to have the same sign and and magnitude at this point and its mirror image. So sigma theta theta, this term is for mode 1 and this term pertains to mode 2. Similarly, sigma rr, which is this stress, has to have the same sign and value above and below the symmetry line. So this is the term corresponding to mode 1 and this is the term corresponding to mode 2. So what we have here are two solutions for mode 1 and mode 2 separately, which are connected to the C11 coefficient and the C21 coefficient. Mode 2 is connected with the C21 coefficient. So now we are going to make a important move. We are going to define two quantities. So we are going to define a quantity called K1, which is root 2 pi r times, we are taking this sigma theta theta at x2 equal to 0, which is same as theta equal to 0. Okay, so that is what we are going to do now, and we are going to define K2 as root 2 pi r sigma r theta at x2 equal to 0. Both of these we are going to def as r tends to 0 at the crack tip. So these two are called the mode 1 and mode 2 stress intensity factor, and so this is the definition of the mode 1 stress intensity factor. Remember, at x2 equal to 0, sigma theta theta becomes sigma yy. So here's your crack. This is x1 r and theta. As x2, this is x2. As x2 tends to 0, sigma theta theta, which is this, on the symmetry line is same as sigma 2 2. Sigma theta theta on the symmetry line is same as sigma 2 2. So you can also write root 2 pi r sigma 2 2 x2 equal to 0. Why do we multiply by root 2 pi r? Because we have this 1 by square root r singularity. The stress is infinite as r tends to 0, but if we multiply by root r on both sides, then sigma, the stress times root r, is a non-singular term that depends only on theta. So at theta equal to 0, as r tends to 0, this quantity this quantity is defined as the mode 1 stress intensity factor, and K2 is this quantity, which is the mode 1 stress intensity factor. If you carry out this limit, if you multiply both sides by root r, this does not depend on r only. This does not depend on r at all. This does not depend on r at all, or none of the terms depend on r anymore. And then you can immediately see that sigma theta theta at x2 equal to 0, which is same as theta equal to 0, is C11 into something, but this is 0. So sigma theta theta depends only on C1. Sigma theta 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 depends only on C1. Sigma RR also depends only on C1. So sigma theta theta is important in mode 1 because it's the opening stress. It's the stress that's trying to open up the crack as it advances. So K1 is the mode 1 stress intensity factor, and it turns out to be C11 times root 2 pi. Similarly, K2 is for mode 2. K2 is for mode 2, and it turns out to be C21 times root 2 pi. So we are now going to replace C11 and C21 in terms of these new constants K1 and K2, which are defined in this way. Okay, so these definitions we are going to use later, but for this problem, for this particular problem, K1 turns out to be C11 root 2 pi and K2 turns out to be C21 root 2 pi. So if we now cast these equations in terms of K1 and K2, then for mode 1, and we write only the symmetric terms. The symmetric terms are the first terms corresponding to C11. So C11 will replace by K1 by root 2 pi. C21 will replace by K2. Now what is the significance of K1? Let's first see what it means mathematically. So you have the crack and you are on the line x2 equal to 0. That means you are on x1, x2 equal to 0, r is same as x1. So as you move along this line, this quantity root 2 pi x1 times sigma 2 2, the value of this quantity as you get closer and closer to the crack gives you K1. Similarly, the value of this quantity as you approach the crack tip gives you K2. On x2 equal to 0, sigma theta theta is sigma 2 2 and sigma r theta is sigma 1 2. We have already discussed that. So you have these two quantities with some physical significance, which are simply replacing the C11 and C21 that you had in the previous equations. So we are just replacing C11 by K1 by root 2 pi and K2 by root 2 pi is replacing C21. So when we do that, we get the symmetric part of sigma theta theta. Remember, the symmetric part of sigma theta theta, is this. We replace C11 by K1 and C21 by K2, and then the symmetric part of sigma theta theta is this, and the antisymmetric part is this. Similarly, for sigma r theta, the symmetric part is this, the antisymmetric part is this, where we have made these two replacements. These two replacements have been made. Now, note something. Sigma theta theta asymmetric corresponds to sigma theta theta for mode 2. And sigma theta theta symmetric corresponds to sigma theta theta for mode 1. So for mode 1, sigma theta theta is maximum at theta equal to 0, that is on the symmetry line. It's maximum at the symmetry line. But for mode 2, sigma theta theta is 0 because of this term. It's 0 on the symmetry line. That is understandable because for the asymmetric case, sigma theta theta has to go from has to change sign at the symmetry line, which means it has to be 0 at the symmetry line. Similarly, sigma r theta for the symmetric case is 0 on the symmetry line because of the sign term, which is again understandable. Remember, sigma r theta is antisymmetric in the mode 1 case, and therefore it has to be 0 on the symmetry line. So sigma r theta is 0 on the symmetry line for the symmetric or mode 1 case. So this is the mode 1 case, whereas it is for asymmetric case or the mode 2 case, it is maximum at the symmetry line. It is maximum at the symmetry line. Also, what you can see is this contains cos, therefore it's a symmetric function. This contains sine times cos, so it's actually an asymmetric function. This is a symmetric function, but this again is an asymmetric function as we would have expected. Okay, so these are the mode 1 and mode 2 stress fields. The dominant terms in the series, remember there was an infinite series from which we only have chosen the dominant term, and these dominant terms for the symmetric case can be expressed. The only unknown in this term is k1. For the asymmetric case, the only unknown is k2. Okay, the only thing that is adjustable in this is k1 and k2. So these are known as single parameter representation of the stress field. So these all are single parameter representations. Okay, so sigma RR, as I said, also can be found. Sigma RR for the symmetric case is this expression at theta equal to 0, that is on the symmetry line. This term is 1, so this thing inside the bracket is 1. So k1 by root 2 pi r cos theta by 2 is the value on the symmetry line. Theta is equal to 0, so this is 1 as well. So k1 by root 2 pi r is the value on the symmetry line. And if you look at sigma theta theta symmetric, on the symmetry line, it's also k1 by root 2 pi r. So on the symmetry line, for the mode 1 case, on the symmetry line, you have sigma theta theta, which is equal to sigma 2 2, equal to sigma RR, which is equal to sigma 1 1. On the symmetry line, the stress state is completely hydrostatic in case of mode 1. Okay, so sigma RR asymmetric is this expression, and it is equal to 0. You can check that it is equal to 0 because of this term on the symmetry line, as we expect from the antisymmetric situation in mode 2. And K1 and K2 are called the mode 1 and mode 2 stress intensity factors respectively. So each of the stress components in mode 1 and mode 2 separately can be denoted in terms of a single undetermined parameter, either K1 or K2. Okay, so that's why it's a single parameter representation. Now, as you can see here, for each of the stress terms, they are separated, variable separated. R has a representation as 1 by square root of r, and there's an angular term. So this is the angular term. Each stress component has a different angular term, and there's a universality here that as you approach the crack tip, all the stresses go to infinity. And if you look at it in 3D, this is how a typical stress component will look. So this is any stress sigma ij will always have this singularity as you get close to the crack. The crack is here. Here is the crack. So here is the crack. At the crack tip, all stresses will go to infinity no matter which direction you approach them from, and this will go to infinity as 1 by square root of r, where r is the distance from the crack tip. Now, this is not a very standard representation of the crack tip fields. We generally represent crack tip fields as color contour plots where the colors represent the level of the stress. So if you look at the opening mode stress fields or mode 1 stress fields, this is how they look in contour plots. So I have arbitrarily used a K1 of 1 to plot this. K1 of 1 has been used to plot this. So these are basically angular functions divided by root r, root 2 pi r, I think. Yeah. So as you can see, the crack is again here. This is the crack. This is the crack here. And this is the crack here. So sigma theta theta and sigma rr are symmetric functions for mode 1. They look symmetric. Whereas sigma r theta is an anti-symmetric function. It is positive here and negative here. It could have been the other way around as well. Okay, if you look at the contour plots for the mode 2 stress fields, you would see that sigma theta theta is now anti-symmetric, sigma rr is now anti-symmetric, and sigma r theta is now a symmetric function as we had expected. So the cracks are again here, here, and here. Okay, so the shapes of the stress fields are important. uh, these this has this somewhat of a circular shape. This is a kidney shaped stress field, and these are basically, remember, since I've taken k1 equal to 1 to plot these are basically the angular functions that I'm plotting. These values, these colors represent levels of the angular function, and the highest color is here where it is equal to infinity. So the same here, same in all the cases, the color coding is the same, and they have these typical shapes which represent basically the shapes of the angular function over the 2D domain. Okay, so this is the mode 2, and you can find the displacement fields as well. So you, from the stresses, you use the constitutive equations to find the strains, and then integrate the strains to get the displacements. So there's a way of doing that, and uh, these are the mode 1 displacement fields, mode 1 displacement fields with this kappa, which is 3 minus nu by 1 plus nu for plane stress and 3 minus 4 nu for plane strain. If you put that, you get either the plane stress displacement field or the plane strain displacement field. The stresses don't care about plane stress or plane strain. They're the same in plane stress or plane strain, but the displacements depend on your choice of approximation, either plane stress or plane strain. The displacement fields for mode 2, I leave that as an exercise, and I'll put it in one of the assignment sheets. You can start from the stresses in mode 2, get the strains using the constitutive equations, integrate them to get the displacements, and then uh, you can find out the the term that I'm sorry, this. So I leave that as an exercise for you. Okay. Uh, so now this is a summary. As I said, you can find the stresses in the find r theta components or r and theta components of the stresses, sigma theta theta rr and r theta, but you can also transfer them into Cartesian components. It depends on what kind of problem you're solving. One or the other set of expressions are convenient to use. So I have summarized all the stresses in terms of Cartesian coordinates. So what I'm writing here is sigma ij as a function of 1 by square root of 2 pi r, okay, and an angular function. The angular functions are different for the different components of stress, and here for mode 1 you will have k1 and mode 2 you will have k2. So this table is important, and these are the angular functions for mode 1 and mode 2. Here I have used x equal to 1, y equal to 2, as is customary. For mode 1, this is the case. For mode 1, you will use k1 here, remember. The root 2 pi r is common between both the modes. And for mode 2, these would be the angular functions. Similarly, for the displacements, the general form of the displacement is this. You have root 2 pi r on the numerator because the displacement actually goes to 0 at the crack tip. Displacements, remember, we have already discussed this, that displacements cannot be infinite at the crack tip or anywhere, because that would violate the small strain assumption. So displacements are not. Displacements depend on root r, and the angular functions are these. So again, we use x and y for 1 and 2. So these are the angular functions for displacements in mode 1. These are the angular functions for displacements in mode 2. It is important to remember that these are very important equations in fracture mechanics, but they are valid very close to the crack tip. And how close to the crack tip are they valid? They are valid as long as the second term in the series, the term that we have chosen, is for n equal to 1. As long as the term n for n equal to 2 is small compared to the term n equal to 1, these equations are valid. As soon as the second term starts gaining in prominence, then these equations are no longer valid. You have to use more terms, and a single parameter representation will not be possible in that situation. When the second term is also significant, then you would have another parameter for the second term. But assuming that the second term is still, you are so close to the crack tip that the second term is insignificant, these equations are useful and indeed very important. So let us try to find the mode 3 fields. Just recall that for this crack, in an infinite body, mode 3 is where you apply sigma 2, 3, 0, coming out of the slide. So it's coming out of the slide on the top and going into the slide at the bottom. And what you are trying to do is the upper part is trying to come out towards you. So U3 is positive here towards you, and U3 is negative here away from you, and that is what is going to make the crack move in a straight line. So it is like tearing a paper. So if you take this piece of paper, here's the crack, and this upper part is moving towards you, lower part is moving away from you, and you are trying to tear it like this. So that is mode 3, where U1 and U2 are 0 all over the plane. U1 and U2 are 0 all over the plane, and U3 can be expressed as a function of x1 and x2 alone. We call that function w. So this is our Navier's equation, which you remember from your elasticity course, is an equation that is obtained by plugging in the strain displacement relations and the isotropic constitutive equations into the equilibrium equation. Now when you do this approximation, you will see that most derivatives of u are equal to 0, except u31 and u32. So if you plug that in, to plug this approximation into the Navier's equation, you get the fact that u3 comma 1 1, second derivative of u3 with respect to x1 and second derivative of u3 with respect to x2 is equal to 0, which means that w satisfies the harmonic equation. So basically the displacement, the out of plane displacements satisfy the harmonic equation in an antiplane shear problem. This is also something that you must have learned in your linear elasticity course. And uh, we again assume a variable separated solution. It's a problem without a length scale, so we assume a variable separated solution like before, where this lambda is what we are going to determine. And this function has to satisfy del square w equal to 0, which is same as this in cylindrical polar coordinates. So this function is plugged in here, leading to a solution, leading to an ordinary differential equation in f theta. And if you solve that, the general solution of w proceeding in a manner uh, absolutely similar to modes 1 and 2, you will get w r theta, which looks like this. Now remember, w is a displacement, not a stress. It has to go to 0. It has to go to 0, but these terms will give rise to stresses if you take their derivatives. This will give rise to a stress which does not depend on r. This will give rise to a stress which depends on root r. All these terms will give rise to stresses that are less dominant than the stress that this term will give rise to. This term will give rise to a stress which is 1 by root r, 1 by square root of r, and so this will give rise to the singular stress term, and these will all give rise to non-singular stress terms as r tends to 0. So we will retain only this part of the expression. We will retain only this part of the expression. And in displacements, this constant term is a rigid body term, so we don't need to worry about it. There are no rigid body displacements. We assume that the whole body has been constrained from moving like a rigid body, so this term is of no consequence to us. So w has a form which is, so w r theta, the most dominant term, most dominant stress term will arise from this displacement. Okay, so the stress that will arise will be 1 by root r, which will be dominant as r tends to 0, just like in cases of mode 1 and mode 2. On the crack faces, sigma theta z has to be equal to 0. Again, look at the crack face normals. The crack face normals remain the same, 0, 1, 0 and 0, minus 1, 0 on the top and the bottom faces. And reason out from the Cauchy relation why sigma theta z has to be 0, or sigma 2, 3 has to be 0 on the top and bottom faces. Now, from the constitutive equation, the only non-zero stresses that will turn out are sigma 3r and sigma 3 theta, and they are given by mu times the strains in the same components of strain. So mu times this is epsilon 3r and this is epsilon 3 theta. These are shear strains that you obtain from u3. So these are functions of u3 or w only, and these are the only non-zero components of stress that you will have. And w, we already have an expression for w. We already have an expression for w, and if you now calculate the stresses, these would be the dominant terms of stresses, and these are the amplitude of these stresses is given by a new constant called the mode 3 stress intensity factor, which has the same definition, same kind of definition as the mode 2 and mode 1 and mode 2 stress intensity factors, but these sigma 3r and sigma 3 theta are the dominant stresses here. The displacement field you can get from wr theta. So what you can do is this constant b naught can be replaced in terms of k3 and will lead to this expression for the displacement close to a crack tip in the mode 3 case. So these are the stresses and displacements for the mode 3 case, and K3 is, as I said, called the mode 3 stress intensity factor. So we have the expressions for the near tip fields in all the three modes. Now, now, what are these good for? So we have made a few assumptions. We have made the most important assumption that we have made is we have retained the most dominant term in the series. We have also dropped terms with negative powers of negative values of n, because those lead to displacements that are infinite at the crack tip. So having made these assumptions, we have derived the mode 1, mode 2 and mode 3 stress and displacement fields separately at the crack tip. You should go through this derivation very, very carefully. This is the crux of linear elastic fracture mechanics. Now, once we have done it, we see that the mode 1 stress field depends on a single parameter K1, the mode 2 stress field on K2, and the mode 3 stress field on K3. These are single parameter representations. What are these single parameters? Why are these undetermined parameters there? Because we have solved a problem which does not have a length scale in it. So we have not specified anything about the external loading that is applied on the boundary of our body. Uh, we have not supplied any information about the length of the crack or any length, width of the body, thickness of the body. No information has been supplied. So even without that, we could come up with a expression for stresses and displacements which depend on only a single parameter. So this single parameter represents the effect of loading as well as geometry on the tip of the crack. So the single parameter can be determined if we know the exact situation of loading and the exact geometry of the body. So this is the medium through which the external boundaries, the external loading and the geometry talk to the crack tip. The crack tip is always has a 1 by square root r singular stress field, no matter what loading you apply. But the amplitude of that distribution will depend on the loading that you apply on the crack tip. Now let us look at, so this is the crux of the single parameter representation. So the effect of everything else, loading and geometry, are clubbed into one single parameter. That's the beauty of this solution. Now now what we need to do is find out uh, how to determine these single parameters. But before that, we would try to see how this single parameter can help us in fracture based design. We'll do that in the next class.